Okay, so we're going to look at a variation of the center problem, the absolute one-center problem. Again, I'm going to restrict my attention to three networks, but this time the functions under consideration are not the weighted distance functions. Rather, they are going to be much more general, arbitrary loss functions. So what we assume here is associated with vertex Vi, we assume there's a loss function. And this is a function of the distance between wherever the center is and vertex Vi. So Fi actually maps the non-negative reals into Fi of 0 and infinity, and we assume Fi is monotone increasing. In distance. Distance is just a number as long as you know the position of the center and the ith vertex. Of course, the ith vertex is at a fixed location. X, the location of the center, is a variable location. Nevertheless, once you pick a particular location, the distance from X to Vi is a known number. So Fi simply maps that number into the non-negative reals. I am going to assume Fi of 0 is again a non-negative number. Okay. So whatever the output of this functional evaluation, that's the loss. That's the loss when Vi is at a distance of this much from the center. So in particular, since now the camera wants me to use both halves, let's just do it this way. In particular, if this is the distance, and if this is the function Fi values as a function of the distance, that number, this is some sort of a monotonic increasing function, such as that. It could be any other shape as well. This is, of course, much more general than the weighted case, where actually in the weighted case, if you have addends, the addend would be the height here, and then you would have a linear increasing function with positive slope. That would be the weight. In this case, this gives you much more generality. For example, if we're talking about, say, a loss due to, say, fire, if this marked point is, for example, a 20-minute worth of distance between X and Vi, then if you get to the if you get to vertex Vi within, say, 20 minutes, the loss is not that much. Of course, it's increasing, but it's perhaps not that much. But after perhaps, say, 20 minutes, all of a sudden, usually, blazes follow, and everything really goes very fast, and your loss could be quite substantial. So after that, it may take off quite in accelerated version. So, or it could be any other type of situation where the loss could be actually any type of loss you can think of. So what we're going to do is I'm going to define my objective function at a point X, which is going to be the position of the center, to be the maximum loss I get from vertices. So for the ith vertex, whatever the distance between X and Vi is, you have that distance, you evaluate your loss function that gives you a certain loss. And whatever the maximum loss is, that gives you the worst loss incurred by placing your center at point X. And what you want to do is you want to minimize f of x over all possible points in a tree network. Okay? That's the problem under consideration. So how are we going to deal with this? That's the problem now. Usually what people do is, if they dare to look at a rather complicated looking problem, they usually make assumptions on the FIs, assuming they're exponential or whatever, and then they play with them and perhaps get some interesting results. Usually, if you're a better scholar, you don't make assumptions unless you're compelled to. You just make assumptions only when you cannot do anything else, of course, because any assumption will move you away from generality as well as from reality, typically. So for that reason, this is a good paper. It's analyzed in a 1977 paper of Francis. There's a related paper due to Deering as well, which is actually, these two are published in the same journal, the Journal of Bureau of Standards, one after the other. The first one is Deering. I think what my guess is, actually Francis was probably referring this particular paper, and then he found out certain results, and then he either wanted to co-author with Deering or perhaps just decided to publish it separately. So they are related papers. But I'm going to mostly focus on that one. And when you study for the exam, you might want to take a look at both. But not necessary. If that's not necessary, Francis's paper is sufficient for the exam, I think. Okay. Anyway, let's continue now. I'm going to make a certain assumption which makes the analysis quite straightforward. And then we'll look at the case without that assumption later. So in the easy case, we assume fi of 0 is 0 for every vertex. Okay? That makes the analysis quite straightforward. Without that, again, the analysis is actually not that difficult, but you have to take care of a lot of technical aspects. With this, if you start taking care of a lot of technical aspects, the main ideas are obscured. That's why I want to give you the main idea first, and then everything will be quite clear. After that, we can take care of the technicalities on the side or subsequently. Okay? All right, so in this situation, our functions look something like this. They always begin at 0, and they so in that case, the domain of the function is 0 to infinity, and the range is also 0 to infinity due to that assumption. Okay? And that's going to permit me to analyze the problem using the so-called neighborhood intersections again. That's going to allow you to do that. Yes?
So I think you assume that the thing is continuous.
Monotone increasing, yes. Let's assume that. Without continuity, we may actually have difficulty not having a minimizing point. So yeah, let's assume it's continuous. That was in the paper. Pardon? No. Well, actually, in this case, the domain and the range, if they are taken to be like this, it's of course bijective. Yes, it's one-to-one. But all monotone functions are one-to-one necessarily. Okay? They don't have to be onto, but they will be one-to-one. Okay. So I can minimize z subject to fi dx vi less than or equal to z for each I, with x being a point in the tree. Let me give names to these. Let's call this, for example, P naught. Let's call this P1. Of course, P0 and P1 are equivalent problems. It's just one that's very standard. Now, my second half of the board. When you look at this, what I want to do is I want to isolate the distance on the left, and I want to have whatever I want to have on the right. And I'm going to do that by applying the inverse function of fi to both sides. When you do that, of course, fi inverse of fi of dx vi will simply output the argument, the distance, and fi inverse of z will be the right side. But to be able to do that, you want to make sure that z is indeed in the domain of definition of fi of inverse. Those are the technicalities. In this case, things are easy. Things are easy if you do the following observation. Observe that f of x is always greater or equal fi of dx vi for any I, which is certainly greater or equal fi of 0, because the distance xvi is non-negative, and because of the monotonicity, of course, this inequality follows. Okay? When you replace the argument with something smaller than itself, of course, the monotonicity will do this. This is true for every I. What's the use of this? That simply tells me that f of x is actually greater or equal to alpha, which is by definition the maximum of my fi zeros. But fi zeros are always 0 in this case. Okay? So alpha is indeed 0 in this particular case. But then later on, of course, when we relax that assumption, alpha will be something else. Okay? That's why I'm giving you the general situation now. So in this case, since f of x, or since the minimum value of this optimization, let's call it z star, whatever the optimizing value is, that's going to be such that it will be something greater or equal alpha, which is greater or equal 0. Okay? Okay. Before I go into those things, first of all, how does the continuity of the continuity assumption on fi's will make sure that there's an optimal solution to this? Anybody see that? When these functions are continuous for a fixed value of z, you're looking at the set of all points x in the network whose function value is less or equal z. That's, of course, a compact subset of the tree. Okay? And when you have a compact subset, of course, when z assumes the minimizing value, whatever that is, well, there will always be a minimizing value, and there will always be a corresponding point. Okay? So the continuity assumption, thanks for reminding me of that, that ensures that there's an optimal solution. And also, when I talked about the inverse function here, that's of course evident because whenever you have monotone increasing functions, you also have their inverses well defined. Okay? All right. So here, when I minimize z subject to these constraints, can I do the following? Minimize z subject to, apply the inverse to both sides, and you get this. I can surely do that if I additionally restrict my z to be greater or equal 0. Well, z will certainly be greater or equal 0 because f of x is always greater or equal 0 because of the above argument here. So at the minimizing value, f of x star, the optimizing point, will still give f of x star greater or equal 0. So I can restrict my z values to numbers greater or equal 0. That's quite evident. Okay? So with that, when z is greater or equal 0, z will be in the domain of definition of the inverse. For that reason, I can rewrite it in this particular form. Okay. Otherwise, of course, you can't. So you need to be careful with these things. All right. So that P2 is equivalent to P1. In other words, if you solve P2, you also solve P1, which means you also solve P0. Now, if you recall your necessary sufficient conditions property 6 from the previous material, the property said that these constraints are consistent or admit a feasible solution for a given value of z if and only if each pair of the distance between each pair of vertices is less than or equal to the sum of the radii associated with those vertices. Okay? So property 6 simply tells you that those constraints will admit or will admit a feasible solution for fixed z if and only if this condition holds true for every pair ij. Now, the condition z being greater or equal to 0 is actually equivalent to having I equals j here additionally. Okay? You might want to relate that on the side. Nevertheless, let's just leave it here this way. So assuming z being greater or equal to 0, this will be true if and only if. Now, you may view the right-hand side as a new function of the argument z. So, this is true if and only if this thing is if you define the function fi inverse plus fj inverse, that's just the name of the new function, by the sum of fi inverse of z plus fj inverse of z, so this new function being evaluated at z, if and only if this holds true for I less or equal j less or equal n again. Okay? Why is the condition z being greater or equal 0 equivalent to having I equals j here? Because when I equals j, that's over here, the distance is 0, and you're looking at fi inverse being plus this one being greater or equal 0, that surely requires z to be greater or equal 0. Okay? So you might want to work on it at home if you wish to. Okay, so where fi inverse plus fj inverse is simply defined to be the first function evaluated at z plus the second function evaluated at z. Equivalently, the distance constraints will admit a feasible solution if and only if. Now, when you look here, what do I know about fi inverse and fj inverse? They are monotone increasing functions. So the sum of two monotone increasing functions is also monotonic increasing. For that reason, the function you see here is monotone increasing, which means it has an inverse. Okay? So I can apply the inverse of that to both sides again. When you do that, you get fi inverse plus fj inverse, and we know that that one exists, evaluated at the distance vi vj. That should be less or equal, what's the right side? Z. And that should be true for I less or equal to j. Okay? So there's only one thing here you need to worry about. Is my distance really in the domain of definition of the new function, the inverse function? Is it or is it not? Let's just justify that. So let's just ask ourselves, is this in the domain of fi inverse plus fj inverse inverse? And the answer, well, you need to look at fi. What's the domain of fi? It's 0, infinity. And this one is also 0, infinity. The range is also 0, infinity. fi inverse has the same domain and range. Then fi inverse plus fj inverse. Now, to evaluate this function at a given argument, that z value must be in the domain of both fi inverse and of fj inverse, but they are the same actually. So the domain here is, again, this way, and the range is this way. Okay? Because at 0, both output 0, so that's why your range is still the same. Now, this simply tells me that the inverse of that function has the domain 0, infinity with range 0, infinity. So the domains and ranges are swapped all the time, but they are the same, so nothing really becomes difficult here, which will not be the case when, of course, you relax that assumption, so you have to take care of that. But the main idea here is, simply utilize the pairwise intersection or the pairwise distance constraints property, okay, to obtain the result here. So what does that tell me? Now that I justified that z being greater or equal, that is well defined because the distance is non-negative and it's in the domain of definition of that function. So I can simply say that hence the minimum z which in our definition is z star, which permits a feasible solution x in the network or in the tree network T is given by, well, for feasibility, z must be greater or equal each of these terms. So the smallest z is how much? It's the maximum of those terms because it should be greater or equal each of those. It's like magic. I like it. It's good. It's good stuff, you know. Because once you know that Horn's lemma holds true, everything follows from actually Horn's lemma. Actually, Horn's lemma, which says that subtrees have a non-empty intersection if and only if every pair of subtrees has a non-empty intersection. That's Horn's lemma. That's a special case of a more general theorem in convex theory. Maybe you might have come across to that. It's called Helly's theorem. Okay? In case you don't know it, make a note of it or a mental note of that. Helly's theorem simply says the following. You might come across to it later. Okay? It says the following. If you have a finite, well, actually it doesn't have to be finite, but let's just say if you have a collection of convex sets in Rn, the n-dimensional space, then their intersection is non-empty if and only if every subcollection consisting of n plus 1 or fewer of the sets have non-empty intersection. Now that simply says that for the case when the number of when the number of convex sets under consideration is less than n, the dimension of the space, it doesn't say anything particularly. Okay? It doesn't give any useful information. But if the number of sets under consideration is much larger than, say, n, in that case, to conclude or to find the intersection, you don't have to look at the entire intersection. You can only look at subset intersections where the subsets have n plus 1 or fewer sets. For n equals 2, for example, what does that say? Well, let's look at the case for n equals 1, the real line. For n equals 1, what does that say? That says you need to look at 2 sets at a time. So that's for the real line. Helly's theorem applies to the real line. Horn's lemma actually generalizes the situation for the real line to a tree network. A tree network is more general than the real line. It's a new space. Okay? All right, so Horn's lemma is a generalization of Helly's theorem applied to the special case of n equals 1. But of course, Helly's theorem also holds true for more general dimensions. That's just a side note. I don't know why I got sidetracked, but that's Horn's lemma or Helly's theorem actually is the deriving machinery behind all this. Without that, you could not do anything, because it doesn't work for general networks, for example. So when you derive results, sometimes it's always good to go back and really ask yourself, well, where does this all come from? It comes from a genesis, something that really generates this, and that's the point here. All right, so here is a very useful information. All you have to do is, if you know what the functions are, then you are able to figure out what their inverses will be. Then you will be able to also figure out what the inverse of the sum of the inverses will be. And all you have to do is, once you figure out what these functions are, evaluate each such function at the distance between pairs of vertices, and that's going to output a number. Whatever those numbers are, the largest of them will give you the optimizing value of z. Okay? Once z star is computed, how do I find actually a point now? We compute or find x star, the optimizing point, or the absolute center, by doing what? By either computing the composite neighborhood representation of the intersection. What's the intersection I want to represent? It's the intersection of the neighborhoods around the vertices vi, where the upper bounds are how much? Fi inverse z star. Z star is now a known number. So Fi inverse of z star is a known number. And when you intersect these neighborhoods, or find the composite neighborhood intersection using the sequential intersection procedure, then you're done. It's going to output some neighborhood whose center will be some point which we have x star, and what is going to be the radius? Again, it's going to be 0. It's going to be unique, because if it's not 0, you can reduce z star by a little bit, which decrease. Did I say increase? You can decrease z star by a little bit, okay, by a positive amount, which will decrease each Fi inverse by a little bit, and which means, of course, you will still have a non-empty intersection, in which case, of course, z star will not be optimum. Okay, so it's really not difficult to argue for that. So that's going to give you a unique point. The uniqueness is, of course, a result of monotonicity. Not non-decreasing, but monotone increasing. If you had non-decreasing functions, that would be different. So be careful with that. In that case, of course, the inverses would not be well defined also, so you would have difficulties. So, sometimes students have a tendency to make generalizations without good justification, so please don't do that, okay? Okay, so that's pretty transparent. Now we will start looking at the general case, but that's the main idea. By the way, before I go into the general case, is that the best way to compute your x star? Anybody suggesting a better method? What did we do in the weighted case, the linear weighted case with addends? We actually identified a pair of vertices whose indices actually determined the value of z star. So you can also use that. So let's just make a note of that. So we may also identify the indices S and T for which Z star is equal to Fs inverse plus Ft inverse distance between S and T, which is greater or equal every other Fi inverse plus Fj inverse. The I equals j case will simply output 0. So in this case, S and T will be distinct. Okay, the minimizing value will be defined by a distinct a pair of vertices whose elements are distinct, and solve the two distance constraint problem having distance x vi, or vi less or equal fi inverse of z star. Z star is a known number now for I equals either s or t. I've got only two vertices under consideration here. So if I find my solution for this pair of constraints, it's going to be necessarily feasible for the rest of the constraints. Okay, you have to say why? Because of the way I actually constructed Z star. It permits a feasible solution. So whatever feasible solution we have for Z star, it must in particular satisfy these two constraints. So you might just solve this, and normally you will get a unique solution here. Once you get a unique solution, that should satisfy all other constraints as well. What unique solution you get here? Well, quite obviously, you get the following unique solution. Let me show it here. If you think of this as the path between Vs and Vt, Vs and Vt are two vertices in the tree. This is the unique path connecting them. Now, there's one function that begins at level Fs of 0 when your point x is on top of Vs, and then it starts increasing in some way. The other one begins at a value of Ft of 0 when your x is on top of Vt, and as you move away from Vt, it increases in some way, right? Like that. And then they meet at some point. When they meet, your f function includes these pieces at least around that particular point. Later on, other I may become dominant or more relevant. So at least locally around that point, that's those are the two pieces that determine the maximum value of f. This will be your x star. This height here will be your z star. That point will be your point x star with height z star or value z star, which is of course equal to f of x star. Okay? And so all you have to do is, how much is this distance now? That portion will be the distance between S and X star, but how much will that be? Yes? Well, I'm solving this, right, for I equals S and T. And the point I'm looking for will surely be on this path, on the path connecting the two. So we're talking about dx star Vs plus dx star Vt being equal to, it's less or equal, but you will have equality, of course. How much? The upper bound, f s inverse of z star plus ft inverse of z star. Okay? Because you're going to obtain equality for both of them. And that's going to be equal to your d vs vt when you solve. Which means that, what does it mean? That means this is actually equal to that, and this is equal to that. So the distance you have here is simply fs inverse evaluated at z star. The other one is similar, okay? I don't know if you see that. Anyway, that's what it is going to be. Okay. Okay, let's take a 10-minute break, and then we look at the general case.